Welcome. Let yourself settle in. There's nowhere you need to be right now, nothing you need to do. Just listen and let these thoughts wash over you like gentle waves. We're going to begin with something vast, something almost impossibly large. We're going to think about where we are, not just here in this room, but where we truly are in the grand cosmic sense. And there's something deeply calming about understanding our place in all of this. Let's start with our solar system. It's our neighborhood in space. The solar system consists of the sun and countless bodies that orbit around it. 8 planets, of course, but also moons, asteroids, comets, dust and ice and rock, all moving together through the void. It's a family of objects, all bound together by gravity, all traveling together through space. And speaking of traveling, our entire solar system is moving. Right now, as you listen to this, we're all on a journey. The solar system takes about 230 million years to complete just one orbit around the center of the Milky Way galaxy. 230 million years. One cosmic year. The last time we were in this exact spot in the galaxy, dinosaurs hadn't even appeared on Earth yet. Think about that for a moment. We're on a voyage that spans timescales almost beyond comprehension. At the center of it all, of course, is the sun, that brilliant star that warms our days. The sun contains 99.86% of the solar system's total mass. Nearly everything, the planets, the moons, the asteroids, all of us, all of that makes up less than 1% of what's out there. We're almost nothing compared to the sun. And yet here we are, thinking about it, understanding it. The scale of the sun is difficult to grasp. If the sun were hollow, if you could somehow scoop out all that burning plasma and gas, you could fit 1 million Earths inside it. 1 million. Imagine a million versions of our entire world, with all its oceans and mountains and cities, all fitting inside that glowing sphere in the sky. Even the sun itself isn't quite the center of everything, though. There's something called the barycenter, the true center of mass of the solar system. Usually it's inside the sun, yes, but because Jupiter is so massive, so incredibly heavy, the solar system's barycenter actually wobbles. Sometimes it shifts outside the sun itself. Jupiter is so large that it tugs everything, even the sun, ever so slightly off-center. They're dancing together, in a way. A slow, graceful dance that's been going on for billions of years. And there's a pattern to all of this motion. All the planets orbit the sun in the same direction. If you could float far above the North Pole of the sun and look down, you'd see all 8 planets moving counterclockwise around it. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, all going the same way, all following the same ancient choreography. It's like a cosmic clock, precise and elegant. But how did all of this begin? How did we end up here, in this particular arrangement, in this corner of the galaxy? That's where our journey takes us next. But for now, just rest in the knowledge of where you are. You're on a small world, orbiting a massive star, in a solar system that's gliding to the Milky Way, all part of something beautiful and vast and infinitely calm. So, how did all of this begin? It's a question humanity has asked for thousands of years. And now, remarkably, we have answers. Not complete answers, perhaps, but enough to paint a picture. A picture of creation on a scale that's both violent and beautiful. The solar system formed around 4.6 billion years ago. 4.5 billion years. It's a number so large it almost loses meaning. But try to hold it in your mind for a moment. Before there were planets, before there was an Earth, before there was a sun, there was only a cloud, a vast, cold cloud of gas and dust, drifting through space. Hydrogen mostly, some helium, tiny grains of dust and ice. Just floating, quiet, dark, but something happened. Maybe a nearby star exploded, a supernova sending shock waves through the galaxy. Maybe it was just a natural pull of gravity, slowly drawing the cloud inward. Whatever the cause, the cloud began to collapse. Slowly at first, then faster. As it collapsed, it began to spin, and as it spun, it flattened like pizza dough twirling in the air, forming a disk, a swirling disk of matter. At the center, where most of the mass concentrated, pressures and temperatures rose, higher and higher, until finally nuclear fusion ignited. The sun was born, and around it, in that spinning disk, the planets began to form. Dust grains stuck together. Pebbles became boulders. Boulders became mountains. Mountains became worlds. Over millions of years, the chaos gradually organized itself into the solar system we know today. But not everything became a planet. Between Mars and Jupiter, there's a region we call the asteroid belt. Millions of rocky fragments orbiting the sun, some as small as pebbles, others as large as mountains. The asteroid belt is a remnant of failed planet formation. It's what's left behind when a planet tried to form, but couldn't quite manage it, and we know why it failed. Jupiter's gravity prevented a planet from forming in the asteroid belt. Jupiter is so massive, so dominant in that region of space, that its gravitational influence stirred up material that was trying to come together. Instead of gently accumulating into a single world, the rocks were flung about, colliding at high speeds, shattering rather than merging. Jupiter essentially stopped a planet from being born. The asteroid belt is the graveyard of what might have been. But Jupiter's influence doesn't stop there. Jupiter is so massive that it creates stable points in space, regions where its gravity and the sun's gravity balance perfectly. We call these Lagrange points. And at two of these points, 60 degrees ahead of Jupiter in its orbit and 60 degrees behind, there are clusters of asteroids. We call them Trojan asteroids. They share Jupiter's orbit, forever traveling with the giant planet like companions on a journey, leading and following, trapped in these islands of gravitational stability. They've been there for billions of years, and they'll remain there for billions more, silent witnesses to Jupiter's power. And beyond all of this, far beyond Neptune, the outermost planet, there's another belt, the Kuiper Belt, a vast ring of icy bodies orbiting in the cold darkness at the edge of the solar system. For a long time, we didn't know it was there. But in 1951, an astronomer named Gerard Kuiper predicted it must exist. Based on mathematics and theory, he said there should be a belt of comets and icy debris out there, beyond the planets. And he was right. 41 years later, in 1992, the Kuiper Belt was finally confirmed. We found it. Another piece of our solar system revealed, another mystery solved. All of this, the sun, the planets, the asteroid belt, the Trojans, the Kuiper Belt, all of it came from that one collapsing cloud. 4.5 billion years ago, there was just gas and dust. Now there are worlds, moons, rings, life. It's a story of creation that took millions of years to unfold, and we're living in the result of it all. Rest in that thought. You are made of matter that was once part of that ancient cloud. The atoms in your body were forged in stars that died before the sun was born. You are quite literally made of stardust. And you're here now, thinking about where you came from. Breathe slowly. Let yourself drift. The story continues, but there's no rush. We have all the time in the world. Let's return to the sun for a moment. We've talked about its size, its mass, its role at the center of everything. But the sun is not just a glowing ball of light. It's dynamic, active. In many ways, it's violent. And yet, even in its violence, there's a kind of beauty, a rhythmic, almost meditative quality to the way it behaves. The sun doesn't rotate the way a solid object would. It's not like Earth, spinning uniformly. The sun is made of plasma, hot, ionized gas, and different parts of it rotate at different speeds. The sun rotates faster at its equator than at its poles. Think about that. The middle spins quicker than the top and bottom. It's almost as if the sun is shearing itself apart, layer by layer. One full solar rotation takes 25 days at the equator. 25 days for a complete spin. But at the poles, 35 days. 10 days longer. This differential rotation twists the sun's magnetic field, winding it up like a coiled spring over time. And eventually, that tension releases in flares, in coronal mass ejections, in all the spectacular phenomena we observe. Here's something that puzzled scientists for a long time. The sun's surface, the part we can see, is about 10,000 degrees Fahrenheit. Hot, certainly. But the sun's corona, the outer atmosphere, the faint halo you can see during a total solar eclipse, the corona reaches millions of degrees. Millions. Far hotter than the surface below it. It's like standing next to a campfire and finding that the air 10 feet away is somehow hotter than the flames themselves. It defies intuition. We still don't fully understand why this happens, though we have theories about magnetic energy and plasma waves. But the mystery remains, floating there in the sky, waiting, and the sun is constantly reaching outward. Solar prominences loop millions of miles into space. These are arcs of glowing plasma, suspended above the sun's surface by magnetic fields. They rise and twist and sometimes erupt, flinging material out into the solar system. When you see images of these prominences, they look almost gentle, graceful loops of light, but each one is larger than several Earths. They're vast beyond imagining, and they're happening all the time. There are even tornadoes on the sun plasma tornadoes. They twist through the sun's atmosphere, spinning columns of superheated gas that can be thousands of miles wide and last for hours or even days. They spiral upward, driven by magnetic forces, beautiful and terrible at once. The sun is not still. It's churning, roiling, alive with motion. But for all its violence, the sun protects us. The solar wind, a constant stream of charged particles flowing outward from the sun, creates something called the heliosphere. It forms a protective bubble around the solar system. This bubble extends far beyond the planets, pushing against the interstellar medium, the thin gas and dust between the stars. The heliosphere shields us from cosmic rays, high-energy particles that would otherwise bombard the inner solar system. We live inside this bubble, protected, surrounded by the sun's influence even in the farthest reaches of space. And at the edge of the heliosphere, something remarkable happens. There's a boundary called the termination shock. It's where the solar wind slows down abruptly, crashing into the interstellar medium like a wave hitting a shore. At this boundary, the termination shock sends energetic particles back inward, reflecting them like a cosmic mirror. Some of those particles make their way back toward the sun, back toward us, carrying information about the edge of our solar neighborhood. The sun is our engine, our protector, our source of light and warmth. But it's also wild, unpredictable, powerful beyond measure. And we orbit it at just the right distance, not too close, not too far, in a zone where water can be liquid, where life can flourish, but closer to the sun. Closer to the sun, world become extreme, scorched, battered by radiation and heat. That's where we're going next. But for now, rest here. Think about the star that makes everything possible. Feel its warmth, even through the vast distance of space. Breathe. Let your thoughts drift like solar wind, outward into the calm. Closer to the sun, worlds become extreme. Let's travel inward now, to the rocky planets, the terrestrial worlds. These are places where conditions push the boundaries of what we think a planet can be. Mercury, Venus, Earth, and Mars, each one unique. Each one shaped by its distance from the sun and the forces that have acted upon it over billions of years. We'll begin with Mercury, the closest planet to the sun. You might think would simply be hot, uniformly scorched by the sun's proximity. But Mercury is a world of extremes in ways you might not expect. Mercury experiences temperature swings from 800 degrees Fahrenheit to negative 290 degrees. 800 degrees on the side facing the sun cold enough to freeze carbon dioxide on the night side. This is because Mercury has almost no atmosphere to hold heat. When the sun sets on Mercury, temperatures plummet. It's a world of fire and ice, depending only on whether you stand in sunlight or shadow. Mercury's relationship with the sun is unusual in another way. It has what's called a 3-to-2 spin-orbit resonance. What does that mean? It means that for every 2 times Mercury orbits the sun, it rotates on its axis exactly 3 times. It's locked in a gravitational dance, a precise ratio that keeps the same rhythm forever. No other planet in our solar system has this particular arrangement. And Mercury is changing even now. Mercury is shrinking as its core cools. The entire planet is contracting, wrinkling like a dried fruit. We can see this in the cliffs and ridges that crisscross its surface. Scars from billions of years of slow collapse. It's getting smaller, inch by inch, over eons. Despite the extreme heat, ice exists in permanently shadowed craters at Mercury's poles. There are places near the poles where sunlight never reaches, deep craters where temperatures remain frigid, and water ice is accumulated, possibly delivered by comets long ago. Ice on the hottest planet, hidden in darkness. And then there's a Caloris Basin, an impact scar that spans 960 miles across Mercury's surface, one of the largest impact craters in the solar system. Some ancient collision, billions of years ago, struck Mercury with such force that it sent shock waves to the entire planet. The Caloris Basin remains, a monument to that violent moment. Now let's move outward to Venus. Venus is the hottest planet. Despite not being closest to the sun, its thick atmosphere traps heat in a runaway greenhouse effect. The surface temperature is around 900 degrees Fahrenheit, hot enough to melt lead, hotter than Mercury, even though Venus is nearly twice as far from the sun. The atmosphere is so dense, The pressure at the surface is like being 3,000 feet underwater on Earth. Venus spins clockwise, opposite most planets. Nearly every other planet in the solar system rotates counterclockwise when viewed from above, but not Venus. It turns the other way, slowly, stubbornly different. We're not entirely sure why. Perhaps a massive impact early in its history knocked it into this backward spin, and Venus spins so slowly. A Venusian day is longer than its year. It takes Venus 243 Earth days to complete one rotation, but only 225 days to orbit the Sun. The year passes before the day ends. Time moves strangely there. But here's something even stranger. Venus' atmosphere superrotates 60 times faster than the planet itself. The clouds race around Venus, whipping through the sky while the planet below turns sluggishly. Winds in the upper atmosphere reach 200 miles per hour, circling the entire planet in just 4 Earth days. We still don't fully understand what drives this superrotation. Venus shows a mysterious ashen light. Observers have sometimes reported seeing a faint glow on the night side of Venus, a dim illumination that shouldn't be there. We're not certain what causes it. Lightning in the clouds, perhaps, or air glow from the atmosphere. It's one of Venus' lingering mysteries. And when Venus passes between Earth and the Sun, an event called a transit, rare Venus transits produce atmospheric shock waves. The passage disturbs Earth's upper atmosphere in measurable ways, sending ripples through the air. These transits are exceedingly rare, coming in pairs separated by over a century. The last pair was in 2004 and 2012. The next won't occur until 2117. A reminder of the slow, patient rhythms of celestial mechanics. Now Earth, home, Earth's magnetic field shields us from solar wind. Without it, the constant stream of charged particles from the sun would strip away our atmosphere, sterilize the surface. The magnetic field deflects these particles, channeling them toward the poles where they create the auroras, the northern and southern lights. We live under an invisible shield, protected, and we're fortunate in another way. Earth's total solar eclipses are a rare cosmic coincidence. The sun is 400 times larger than the moon, but it's also 400 times farther away. So from Earth, they appear almost exactly the same size in the sky. This perfect match allows the moon to completely cover the sun during a total eclipse, revealing the corona. No other planet in the solar system experiences such perfect eclipses. It's an accident of geometry and timing that won't last forever, because the moon is leaving us. Slowly, yes, but measurably. The moon recedes from Earth by 3.8 centimeters per year. It's moving away, pulled by the same tidal forces that it exerts on our oceans. In the distant future, total solar eclipses will no longer be possible. The moon will be too far away, too small in the sky. But for now, we also have lunar eclipses. When the moon passes through Earth's shadow, lunar eclipses turn the moon red via refracted sunlight. The light bends through Earth's atmosphere, filtering out the blues and greens, leaving only the reds to illuminate the moon. It glows like a dim ember in the sky. Blood moon, some call it, but there's nothing ominous about it. It's just light taken the long way around. And finally, Mars, the red planet. Mars is planet-wide dust storms lasting months. Sometimes a small storm will grow, feeding on itself until it engulfs the entire planet in a choking haze. The sky turns orange-red, The sun dims to a pale disk. These global storms can last for months before finally subsiding. We watched one unfold in 2018, swallowing everything. Mars is home to Olympus Mons, the tallest volcano in the solar system. It rises 16 miles above the surrounding plains, 3 times the height of Mount Everest. So wide at the base that if you stood on its slopes, you wouldn't see the summit. It would be beyond the horizon, a mountain so vast it challenges comprehension. And there's Valles Marineris, a canyon system that stretches over 4,000 kilometers across Mars' surface. If placed on Earth, it would span the entire United States. In places, it's 7 miles deep. The Grand Canyon would be lost inside it. Locked in Mars' polar caps is water ice mixed with frozen carbon dioxide. Mars' polar caps could flood the planet if melted. There's enough water there to cover the entire surface in liquid, perhaps 30 feet deep. Mars was once a wetter world, and the evidence is frozen at its poles. Mars has 2 small moons, Phobos and Deimos. Phobos is so close to Mars and orbits so quickly that Phobos rises and sets twice daily. Imagine watching a moon rise in the west, arc across the sky, and set in the east. Then do it all over again before the day ends. Phobos is spiraling inward, doomed to crash into Mars or break apart in perhaps 50 million years. And because Mars' moons are so small, Mars experiences only partial solar eclipses. The moons can't cover the sun completely. They pass across it like dark spots, brief shadows, but never the total darkness we experience on Earth. These inner worlds, scorched, frozen, stormy, geologically alive, each one a study in extremes. Each one a reminder that planets are not gentle places. They're shaped by violence and time and the relentless physics of the cosmos. Rest now. Let these worlds turn in your mind. We'll journey outward soon, to even stranger places. But there's no hurry. The planets have been there for billions of years. They'll wait. Let's journey outward now, past the asteroid belt, beyond the realm of rock and metal. Out here, the planets are different, massive, made not of solid ground, but of gas and liquid, swirling storms and crushing pressures. These are the gas giants. Colossal monsters of our solar system. We'll begin with Jupiter, the king of planets. Jupiter could fit over 1,000 Earths inside, more than 1,000. If Earth were a marble, Jupiter would be a basketball. It's so large that it almost became a star itself. If Jupiter had been just a bit more massive, nuclear fusion might have ignited in its core, and we'd live in a binary star system. But it fell short. Instead, it became the largest planet, dominating everything around it. And Jupiter moves. Jupiter spins fastest of all planets. Despite its enormous size, it completes one rotation in less than 10 hours. 9 hours and 55 minutes, to be precise. This rapid spin stretches Jupiter outward at its equator, making it visibly flattened. The clouds race across its face in bands of color. Browns, whites, oranges, churning in endless motion. And there, in Jupiter's southern hemisphere, is the most famous storm in the solar system. The Great Red Spot has raged for 350 years or more, possibly much longer. We've been observing it since the 1600s, and it shows no signs of stopping. It's a storm larger than Earth itself, winds howling at hundreds of miles per hour, a vortex that has outlasted empires and civilizations. Recently it's been shrinking, growing smaller over the decades. But even diminished, it remains vast. A reminder of Jupiter's power. Jupiter's influence extends far beyond its clouds. Jupiter's magnetosphere is larger than the Sun. The magnetosphere, the region of space dominated by Jupiter's magnetic field, stretches millions of miles into space. If we could see it with our eyes, it would appear larger than the Sun in our sky, even from Earth's distance. It traps charged particles, creating intense radiation belts that would be lethal to any spacecraft lingering too long. The moons that orbit close to Jupiter are bathed in this radiation constantly. And deep inside, beneath the clouds, beneath layers of hydrogen and helium compressed by unimaginable pressure, Jupiter's core may be rocky, surrounded by metallic hydrogen. Metallic hydrogen, a state of matter so exotic it can barely be created in laboratories. Under the crushing weight of Jupiter's mass, hydrogen is squeezed until it behaves like a liquid metal, conducting electricity, generating the planet's powerful magnetic field. And at the very center, perhaps a core of rock and ice, Earth-sized or larger, hidden beneath thousands of miles of compressed gas. Now let's continue outward to Saturn, the ring jewel of the solar system. Saturn is even less dense than Jupiter. In fact, Saturn's density is so low it could theoretically float on water. If you could find an ocean large enough, Saturn would bob on the surface like a beach ball. It's made almost entirely of hydrogen and helium, puffed up and light despite its tremendous size. And those rings, Saturn's magnificent rings, they look solid from a distance, but they're not. Saturn's rings are mostly water ice, billions of individual chunks of ice, ranging from tiny grains to house-sized boulders, all orbiting Saturn in a thin, flat plane. They shimmer and reflect sunlight, giving Saturn its distinctive appearance. We're not entirely sure how old the rings are. They may be ancient, left over from Saturn's formation, or they may be relatively young, perhaps the remains of a moon that wandered too close and was torn apart, because there's a limit to how close something can orbit. The Roche limit keeps Saturn's rings from forming moons. Inside this boundary, tidal forces from Saturn are stronger than the gravity holding a moon together. Any object that crosses this line will be pulled apart, stretched and shredded by the competing gravitational forces. The rings exist inside this limit. The particles want to come together, but Saturn won't let them. They're trapped in this state, frozen between becoming something and remaining as they are. And Saturn has storms too. At its north pole, there's something utterly bizarre. Saturn's hexagon storm spans 20,000 miles. It's a six-sided jet stream, a perfectly geometric shape that has persisted for decades. Each side of the hexagon is wider than Earth. We've never seen anything like it anywhere else. The winds trace this shape with eerie precision, turning at sharp angles, maintaining the pattern. We have theories about why it forms, standing waves in the atmosphere, interactions between jet streams, but the hexagon remains one of Saturn's most mesmerizing mysteries. Saturn spins rapidly, too, though not quite as fast as Jupiter. Saturn's day lasts 10.7 hours, causing extreme flattening. The centrifugal force from this rapid rotation pushes the equator outward, making Saturn the most oblate, the most squashed of all the planets. It's noticeably flattened even in photographs. The poles are pulled inward while the equator bulges outward, a world stretched by its own spin. These gas giants, Jupiter and Saturn, they're not places you could ever stand on. There's no surface. If you descended into their atmospheres, You fall through layers of gas that gradually become denser, then liquid, then perhaps something stranger still, until finally the pressure would crush you long before you reach whatever lies at the center. They're worlds without ground, planets that are more like small stars that never ignited, and yet they're beautiful. The bands of clouds, the storms that dwarf our entire planet, the rings catching sunlight, the moons orbiting by the dozens. They're alien in the truest sense, but they're part of our neighborhood. They've been here all along, spinning in the darkness, waiting for us to notice them. Let your mind rest on that image. Saturn, with its rings spread wide, slowly turning against the stars. Jupiter, with its great red spot, a storm older than any human civilization. Vast, patient, eternal. There are stranger worlds still farther out, but we'll visit those soon enough. For now, drift here among the giants. Let their slow rotation lull you. There's no rush. Space is patient. The planets will wait. Breathe deeply. Let go. Rest. Beyond the gas giants, in the cold outer reaches of the solar system, there are two more worlds. Smaller than Jupiter and Saturn, yes, but no less fascinating. These are the ice giants, Uranus and Neptune, distant, frigid, and profoundly strange. Let's begin with Uranus. Uranus is tilted, dramatically so. While most planets spin like tops, their axes roughly perpendicular to their orbits, Uranus rotates on its side due to an ancient collision. At some point in the distant past, billions of years ago, something massive struck Uranus. The impact was so violent it knocked the entire planet over. Now Uranus rolls through space like a ball, its axis tilted 98 degrees. Its poles point where most planets' equators would be, and this creates something truly bizarre. Uranus poles experience 42 long days and nights because of the extreme tilt. When one pole points toward the sun, it stays pointed that way for decades as Uranus completes nearly half its orbit. 42 years of continuous sunlight. Then, as Uranus continues around the sun, that pole tilts away into shadow and begins 42 years of continuous darkness. The equator, meanwhile, experiences more normal day-night cycles, but the poles live in a world of endless extremes. In fact, because of this tilt, Uranus poles receive more sunlight than its equator over the course of a Uranian year. You'd think the equator would be warmest, as it is on Earth. But on Uranus, the geometry is reversed. The poles bask in decades of sunlight, while the equator receives only glancing rays. It's a world turned on its head, literally. Uranus appears as a pale blue-green disk through telescopes. Calm, featureless, mostly. Its atmosphere is composed of hydrogen, helium, and methane, with the methane giving it that distinctive color. Beneath the atmosphere, there's likely a mantle of water, ammonia, and methane ices. Not ice as we know it, but hot, compressed, and exotic. And deeper still, perhaps a rocky core. But Uranus keeps its secrets. It's one of the least explored planets. Only one spacecraft, Voyager 2, has ever visited, and that was just a brief flyby in 1986. Now let's travel even farther out, to Neptune, the last of the major planets, the most distant world in our sun's family. Neptune is active in a way that surprises us. Despite being so far from the sun, despite receiving so little sunlight, Neptune emits more heat than it receives. It radiates about 2.5 times more energy into space than it absorbs from the sun. Where does this heat come from? It's still generating warmth from its formation, perhaps, or there are internal processes we don't fully understand: gravitational compression, chemical reactions deep in its interior. Neptune is warm in its own cold way, glowing faintly with its own internal fire. And this internal heat drives something remarkable. Neptune's winds reach 1,300 miles per hour, the fastest winds in the solar system, faster than any hurricane on Earth, faster even than the speed of sound in Earth's atmosphere. These winds scream through Neptune's upper atmosphere, whipping clouds into streaks and bands. The planet is a cauldron of motion, powered by forces we're only beginning to comprehend. Neptune appears as a deep, rich blue. Neptune's blue color comes from methane absorption. Methane in the atmosphere absorbs red light, allowing the blues to reflect back. It's a similar process to what colors Uranus, but Neptune's blue is more vivid, more saturated. It's a beautiful world, serene in appearance, violent in reality. And here's something almost magical. Deep inside Neptune, under the immense pressures of the interior, carbon from methane may be compressed into diamond. Neptune's excess heat may be linked to diamond rain. Imagine it, diamonds forming in the crushing depths, then sinking slowly toward the core like glittering rain, releasing gravitational energy as they fall. This energy could contribute to Neptune's internal heat. We can't observe this directly, of course, but laboratory experiments suggest it's possible. Neptune may have a layer where diamonds precipitate from the sky, accumulating over eons into a shell of crystallized carbon around the core. It's one of the most enchanting ideas in planetary science. A rain of diamonds falling to the dark interior of a distant world, never seen by human eyes, happening now, as it has for billions of years. Uranus and Neptune, the ice giants, tilted and stormy, cold and yet strangely warm, hiding diamonds and mysteries in their depths. They orbit so far from the sun that they're almost in a different realm entirely. The sunlight that reaches them is faint, the temperature's barely above absolute zero, and yet they persist. They endure. They remind us that planets can exist in forms we might never have imagined. These worlds are so distant that they're easy to forget. But they're there, turning slowly in the darkness, waiting. Voyager 2 visited them decades ago and sent back our only close-up images. Since then, they've been largely alone, observed only by telescopes from across the solar system. But they're not empty. They have moons, rings faint and dark, weather systems that rage and evolve. They're alive in their way, as alive as any planet can be. Let yourself drift outward with these thoughts. Imagine standing on a moon of Neptune, looking up at that blue giant filling the sky, knowing that deep beneath those clouds, diamonds are raining down. Imagine the silence, the cold, the distance from everything familiar. And yet there's beauty there, strange beauty. Rest now. Let the ice giants turn in your mind. We're near the edge of the solar system now, but there's still more to see. Strange objects in the darkness. Visitors from the deep, but that can wait. For now, just breathe. Let the quiet of deep space settle over you. The planets turn. The universe continues. And you're here, thinking about it all, connected to these distant worlds by nothing more than curiosity and wonder. We've talked about the planets. But the planets are not alone. Orbiting them, caught in their gravitational embrace, are moons. Hundreds of them. Over 200 moons orbit planets in the solar system. Some are tiny, irregular chunks of rock. Others are worlds in their own right, larger than some planets, with atmospheres and geology and mysteries that rival anything we've found elsewhere. These moons, these are where some of the most exciting discoveries are happening, because some of them may harbor life. Let's start with Io, one of Jupiter's four largest moons. Io is the most volcanically active body in the entire solar system. Io has over 400 active volcanoes. 400. Its surface is constantly being resurfaced by lava flows, sulfur deposits, and eruptions that send plumes hundreds of miles into space. The entire moon is being turned inside out by volcanic activity. Why is Io so active? Jupiter's immense gravity stretches and squeezes Io as it orbits, generating tremendous internal friction. This tidal heating keeps the interior molten, driving the endless volcanism. Io is caught in a gravitational tug-of-war between Jupiter and its neighboring moons, and the result is a world on fire. Now let's move to Europa, another of Jupiter's large moons. Europa looks cold. Its surface is a shell of water ice, cracked and ridged like a frozen lake. But beneath that ice, Europa hides a salty ocean beneath ice. A global ocean, perhaps 60 miles deep, warmed by tidal heating, just like Io. But instead of driving volcanoes, the heat keeps water liquid. And where there's liquid water, there might be life. Europa is one of the best candidates in the solar system for finding extraterrestrial life. Beneath that ice in the darkness, there could be hydrothermal vents, chemical energy, perhaps even simple organisms. We don't know yet, but missions are being planned to visit Europa, to study its ocean, to search for signs of life in the deep. Farther out, orbiting Saturn, is a tiny moon called Enceladus, and Enceladus is extraordinary. Enceladus ejects icy plumes from a subsurface ocean. At its south pole, there are great geysers shooting water ice and vapor into space. The Cassini spacecraft flew through these plumes, tasted them, analyzed them, and what it found was remarkable. Water, salt, organic molecules, everything you'd need for life. These plumes come from an ocean beneath Enceladus' icy crust, and they don't just fall back to the surface. Enceladus tiger stripes fuel Saturn's earring. The ice particles escape Enceladus' weak gravity and spread out into a faint ring around Saturn, the earring, fed continuously by this tiny moon's geysers. Enceladus is painting Saturn's space with its ocean, particle by particle. And then there's Titan, Saturn's largest moon. Titan is bigger than the planet Mercury, and it's unlike anywhere else in the solar system. Titan has rivers, lakes, and rain of methane, not water. Methane. On Titan, it's so cold that methane acts the way water does on Earth. It evaporates, forms clouds, rains down, carves river channels, pools into lakes and seas. There are entire hydrocarbon seas on Titan, liquid methane and ethane, lapping against shorelines of water ice as hard as rock. Titan's atmosphere is denser than Earth's. Thicker, even. The pressure at Titan's surface is 1.5 times Earth's sea level pressure. The atmosphere is mostly nitrogen, like ours, but with methane and complex organic chemistry happening constantly. Titan is shrouded in orange haze, opaque to visible light. We can only see the surface with radar or infrared imaging. Titan may have a subsurface ocean of water too, beneath its icy crust, beneath the lakes of methane. A hidden ocean like Europa and Enceladus. Titan might be 3 worlds in one. Methane, whether on the surface organic chemistry in the atmosphere, and a water ocean deep below. Back at Jupiter, there's Ganymede, the largest moon in the entire solar system, bigger than Mercury. And Ganymede is unique. Ganymede generates its own magnetic field. It's the only moon known to do this. Deep inside, Ganymede has a liquid iron core, and the motion of that core creates a magnetic field, just like Earth's. Ganymede has its own magnetosphere, nested inside Jupiter's larger one. It's a moon that behaves, in some ways, like a planet. And there's Callisto, the outermost of Jupiter's large moons. Callisto is ancient, heavily cratered. Its surface is one of the oldest in the solar system, largely unchanged for billions of years. Callisto's surface hints at hidden impacts. Beneath the craters, there may be a subsurface ocean here too, kept liquid by residual heat and the decay of radioactive elements. Callisto is quieter than its siblings, less dramatic, but it holds its secrets just the same. At Uranus, there's a small moon called Miranda, and Miranda is bizarre. Miranda shows signs of ancient destruction. Its surface is a chaotic jumble of terrains, cliffs, valleys, ridges that don't seem to belong together. It looks like it was shattered, then reassembled, the pieces fitting together in strange ways. Perhaps it was broken apart by a massive impact. Then its own gravity pulled it back together. Or perhaps tidal forces warped and cracked it. Miranda is a puzzle we haven't solved. And orbiting Saturn, there's Iapetus, a two-tone world. Iapetus has a black and white surface. One hemisphere is bright, icy, reflective. The other is dark as coal. The contrast is stark, visible even through small telescopes. We think the dark material may be debris from other moons, accumulated on Iapetus' leading hemisphere as it orbits. But the exact mechanism is still debated. Iapetus has another mystery. Running along its equator is a massive ridge, thousands of miles long, 12 miles high in places. Iapetus' equatorial ridge may be a collapse ring. Perhaps Iapetus once had a ring system, like Saturn, and over time the ring material fell to the surface, piling up along the equator. Or perhaps it's from ancient tectonic activity, the moon's crust buckling as it cooled. Either way, Iapetus is strange, a moon unlike any other. And finally, Neptune's largest moon, Triton. Triton orbits Neptune backward. It's the only large moon in the solar system that orbits retrograde, opposite to its planet's rotation. This tells us Triton wasn't born around Neptune. It was captured. Triton is likely a Kuiper Belt object, something like Pluto, that wandered too close to Neptune and was snared by its gravity. Triton is geologically active too. It has geysers, erupting nitrogen gas and dark organic material that streak across its surface. It's one of the coldest objects in the solar system, and yet it's not dead. It's changing, evolving even now. These moons, they're not just satellites. They're worlds. Volcanic worlds, ocean worlds, methane worlds, captured worlds, shattered and reassembled worlds. They orbit in the shadows of their planets, often overlooked, but they're some of the most interesting places in the solar system. And some of them, Europa, Enceladus, Titan, some of them might harbor life, not intelligent life. Perhaps, but life. Microbes in the darkness of subsurface oceans. Organisms feeding on chemical energy from hydrothermal vents. Simple, yes, but life nonetheless. It would mean we're not alone, not in the universe, but right here in our own solar system. life in the oceans of distant moons, hidden beneath ice, waiting to be found. Rest in that possibility. Let it comfort you. The universe may be more alive than we know. There may be life out there, swimming in the dark, unaware of us, just as we're still searching for it. Breathe slowly. Let these moons turn in your thoughts. There are more wonders still, but we'll come to them gently. For now, just drift. The moons are patient. They waited billions of years. They can wait a little longer. All is calm. All is well. We've traveled far now, past the planets, past the great moons. Out here at the edge of the solar system, the sun is just a bright star among stars. The distances are almost incomprehensible, and yet there are still worlds here. Small worlds, yes, dwarf planets, we call them, but worlds nonetheless, each with its own character, its own story. Let's begin with Pluto, once considered the ninth planet, now reclassified, but no less fascinating for it. Pluto's orbit carries it over 3.6 billion miles from the Sun at its farthest point. 3.6 billion miles. The sunlight that reaches Pluto is faint, barely more than bright moonlight on Earth. It's a cold, distant place, on the very frontier of what we can easily observe. And Pluto surprised us. When the New Horizons spacecraft flew past in 2015, we expected a dead, cratered world. Instead, we found a planet that's geologically active, even now. Pluto has mountains of water ice as hard as rock, rising miles into the thin atmosphere. It has plains of frozen nitrogen, smooth and young, resurfaced within the last few million years. And there's Pluto's heart, a vast plain of nitrogen ice, shaped like a heart, bright and smooth. Pluto's nitrogenized heart expands and contracts. During Pluto's long year, 248 Earth years, as different regions tilt toward or away from the faint sun, the nitrogen ice sublimates, turning from solid to gas, then refreezes elsewhere. The heart breathes, in a sense, expanding and shrinking with the seasons, and that nitrogen ice flows. Pluto's glaciers flow downhill, just like glaciers on Earth, but made of frozen nitrogen instead of water. They creep across the surface, carving the landscape, filling in craters. Pluto is not a static world. It's changing, slowly, driven by processes we're only beginning to understand. Pluto's day lasts 6.4 Earth days. It rotates slowly, locked in synchronous rotation with its largest moon, Charon. Pluto and Charon are tidally locked to each other, always showing the same face. They orbit each other like a binary system, a double planet, dancing together in the darkness. But Pluto is not the only dwarf planet out there. Farther still, there's Eris. Eris is more massive than Pluto. In fact, the discovery of Eris in 2005 was one of the reasons Pluto was reclassified. If Pluto was a planet, then Eris should be too, and there might be dozens more like them. So the definition of planet was revisited, and Pluto became the prototype of a new category, dwarf planets. Eris orbits even farther out, in the scattered disk, a region beyond the Kuiper Belt. At its most distant, Eris is nearly 100 times farther from the Sun than Earth. It takes 557 years to complete one orbit. It's covered in methane ice, bright and reflective, one of the whitest objects in the solar system. And then there's Haumea, a dwarf planet with a truly strange shape. Haumea spins so fast it's football-shaped, It completes one rotation in less than 4 hours, the fastest spin of any known large object in the solar system. The centrifugal force from this rapid rotation has stretched Haumea into an elongated ellipsoid, shaped like a rugby ball. It even has rings, discovered just recently, a tiny, spinning world with rings, tumbling through the outer solar system. There's Makemake, another Kuiper Belt dwarf planet, reddish in color, covered in frozen methane and nitrogen. Makemake lacks a detectable atmosphere. Any gases that might have once surrounded it have long since escaped or frozen onto the surface. It's airless, silent, a frozen world slowly circling the distant sun. And then there's Ceres, the odd one out. Ceres doesn't orbit in the Kuiper Belt. It's in the asteroid belt between Mars and Jupiter. It's the largest object in the asteroid belt, large enough to be rounded by its own gravity. And so it's classified as a dwarf planet too. For a long time, we thought Ceres was just a big rock, but the Dawn spacecraft visited Ceres and revealed something unexpected. Ceres contains briny subsurface water. Beneath its surface, there's a layer of salty, liquid water, or at least a briny slush. Ceres may even have had a subsurface ocean in the past, and some of that water might still be liquid today. And on Ceres' surface, there are mysterious bright spots. Ceres' bright spots are salt deposits. When water from the interior reaches the surface through cracks or impacts, it evaporates, leaving behind bright patches of salt. The most famous are Necator Crater, gleaming white against the dark gray of Ceres' surface, evidence of recent geological activity, of water moving beneath the surface even now. Ceres, Pluto, Eris, Haumea, Makemake, these are just the ones we've named and studied. There are likely hundreds more dwarf planets out there, waiting to be discovered. Small worlds in the darkness, each one unique, each one holding clues to the formation of the solar system. They orbit at the edge, where the sun's influence fades, where space begins to blend into the realm between stars. But they're still part of our family. They form from the same cloud of gas and dust as Earth, as Jupiter, as everything else. There are distant cousins, cold and remote, but connected, and there's something peaceful about them. They're not dramatic like Jupiter's storms or Io's volcanoes. They're quiet, patient. They've been out there for billions of years, largely unchanged, waiting in the cold and the dark. Some of them we visited once, briefly. Most we've only observed from afar, as points of light moving slowly against the stars. But they remind us that the solar system doesn't end with Neptune. It extends far beyond, into regions we're only beginning to explore. The Kuiper Belt, the scattered disk, the distant detached objects. There's so much more out there than we once imagined. Let yourself drift out to these distant places. Imagine the silence, the cold, the faint sun, barely brighter than the stars around it. Imagine standing on Pluto, looking up at that heart of nitrogen ice, watching the slow movement of glaciers over centuries. Or standing on Haumea, feeling the rapid spin, the strange pull of a world shaped by its own rotation. These places are real. They exist right now, out there in the darkness. And someday, perhaps, we'll visit them again. We'll send probes or even people to explore these distant shores. But for now, they wait, quiet, patient, timeless. Rest in that quietness. Let the dwarf planets turn slowly in your mind. We're almost at the edge now, almost at the place where the solar system fades into the unknown. But there's a little more to see, just a little more. We've reached the frontier now, the edge of everything we think of as the solar system. Out here, the rules change. The sun is a distant point of light, darkness and cold rain. And yet, there are still things here. Vast populations of objects, ancient and untouched, waiting in the outer dark. Let's begin with the Kuiper Belt. We've mentioned it before, but now we're here. The Kuiper Belt contains icy remnants beyond Neptune. It's a disk of objects stretching from Neptune's orbit outward, perhaps twice as far again. Millions, maybe billions of icy bodies. Some are tiny, no larger than a house. Others are dwarf planets, like Pluto and Eris. These objects are leftovers, remnants from the formation of the solar system that never came together to form a planet. Out here, so far from the sun, there wasn't enough material, or perhaps Jupiter's influence disrupted things before a planet could form. So they remain, frozen in time, pristine samples of the early solar system, largely unchanged for 4.5 billion years. But the Kuiper Belt has a mystery. As we look farther out, we expect to keep finding objects. The belt should gradually fade, thinning slowly with distance. But it doesn't. The Kuiper Cliff marks a sudden drop in objects. At about 50 astronomical units from the Sun, 50 times Earth's distance, the number of objects drops sharply. Suddenly, there's a cliff in the distribution, and we don't know why. Perhaps there is something out there, some massive object that cleared out the region. Or perhaps it's just the way the solar system formed, a natural boundary where the disk of material simply ended. We're not sure. The Kuiper Cliff is still an open question, a mystery at the edge of the known. Beyond the main Kuiper Belt, there's another region, the scattered disk. This is where objects have been flung into eccentric, tilted orbits by gravitational interactions with Neptune. They loop far out into space, then swing back in, passing to the inner regions before heading out again. The scattered disk supplies short-period comets. When one of these objects gets nudged just right, it can fall into the inner solar system, becoming a comet. Its ice is subliming the sun's heat, creating that characteristic tail of gas and dust. We've seen these comets throughout history. Halley's Comet, returning every 76 years. Others that visit once and never return. They're visitors from the outer darkness, carrying messages from the edge of the solar system, giving us glimpses of conditions out there. But even the scattered disk is not the end. Farther still, much, much farther, there is the Oort Cloud. The Oort Cloud begins about 1 light year away. 1 light year. That's the distance light travels in an entire year. That's about 6 trillion miles. A quarter of the way to the nearest star. The Oort Cloud is so far out that it's barely bound to the sun objects that orbit so slowly, so distantly, that a single orbit takes millions of years. We've never actually seen the Oort Cloud. Not directly. It's too far, too faint, too diffuse. But we infer its existence from the long-period comets that occasionally fall toward the sun. These comets come from random directions, with orbits that suggest they originated far, far out. They're visitors from the Oort Cloud, disturbed by the gravity of a passing star or the tidal pull of the galaxy itself, falling inward after billions of years in the cold. And the Oort Cloud is vast. It contains trillions of icy bodies. Trillions, more than we can easily imagine. Each one a small world, a chunk of ice and rock, drifting in the dark. Most will never come close to the sun. Most will orbit in the outer darkness for the entire lifetime of the solar system, never warmed, never disturbed. The Oort Cloud is a sphere surrounding the solar system in all directions. It's not a disk like the Kuiper Belt. It's a shell, a vast bubble of dormant comets, marking the true edge of the sun's gravitational domain. Beyond the Oort Cloud, the sun's influence fades to nearly nothing. Beyond that, interstellar space, the realm between stars. Think about that for a moment. The solar system is so much larger than we typically imagine. We think of the planets, maybe out to Neptune, but the true solar system extends a light year or more. It's enormous, and most of it is empty, dark, cold, inhabited only by these silent, icy sentinels. The Oort Cloud has been there since the beginning, formed from the same primordial material as everything else, scattered outward by gravitational interactions with the giant planets. It's ancient, undisturbed, a fossil record of the solar system's birth, and it will be there long after we're gone, long after the sun swells into a red giant and consumes the inner planets. The Oort Cloud will remain, orbiting the dying star, and when the sun finally fades to a white dwarf, a cold ember in space, the Oort Cloud will still be there, slowly dispersing over billions of years, but never truly gone. There's something humbling about that. We live on a tiny world, warmed by the sun, full of life and activity, but the solar system extends so far beyond us. Most of it is empty space and frozen silence. And yet it's all connected. The same gravity that holds us to Earth extends out to the Oort Cloud, tenuously, weakly, but still there. We are part of something vast. The solar system is our home, all of it, not just Earth. From the sun's burning core to frozen comets a light year away, it's all one system, one family, bound together by gravity and shared origin. Rest in that vastness. Let your mind drift outward, to the edge of the Oort Cloud, to the boundary between the solar system and interstellar space. It's so far away that light takes a year to travel there, and yet it's still home, still part where we come from. Out there in the darkness, trillions of icy worlds wait. They don't know we're here. They don't know anything. They just orbit silently, patiently, as they have for billions of years. And perhaps someday we'll send something out there. A probe, a signal, a message, something to mark our presence, to say, we were here, we wandered, we reached out to the edge of everything we could reach. But for now, the Oort Cloud remains untouched, a frontier we've barely begun to explore, a reminder that there are still mysteries, still unknowns, still places we haven't been. Breathe deeply. Let the silence of the outer solar system settle over you. There's no sound out there, no air to carry it, just a slow, eternal motion of objects in the dark, orbiting the distant sun. You're safe here, warm, surrounded by air and light and life. But knowing that the darkness is out there, that the solar system extends so far, it puts things in perspective. We're small, yes, but we're also part of something magnificent. Rest now. Let go. Drift in the quiet. The Oort Cloud will be there, waiting at the edge of everything. All is calm. All is well. The universe continues, patient and eternal. Sleep if you like. The journey is nearly complete, but there's no rush. Time moves differently out here. 1,000,000 years is nothing. An orbit takes longer than human civilization has existed. Just breathe. Just be. Let the vastness hold you gently, like a lullaby from the stars. Let's return inward for a moment, back from the Oort Cloud, back toward the sun, to talk about the visitors, the wanderers, comets, and the missions we've sent to meet them. Comets are messengers from the outer darkness. They spend most of their lives in the cold, frozen, and dormant. But occasionally, something disturbs them, a gravitational nudge, a passing star, and they fall inward toward the sun. As they approach, the sun's heat begins to work on them. The ice sublimates, turning directly from solid to gas, and a coma forms around the nucleus, a glowing cloud of gas and dust. A tail streams behind, pushed by the solar wind and radiation pressure, always pointing away from the sun. We've studied comets from Earth for millennia, but in recent decades, we've sent spacecraft to visit them up close. And what we've learned is remarkable. In 2014, the Rosetta spacecraft arrived at Comet 67P, a small comet shaped like a rubber duck tumbling through space. Rosetta orbited the comet for 2 years, watching it come alive as it approached the sun. And one of the things Rosetta discovered was the smell. Comet 67P smells like rotten eggs. The instruments detected hydrogen sulfide, ammonia, methane, and other organic compounds. If you could somehow stand on the comet and take a breath, though you'd die instantly in the vacuum, but if you could, it would smell terrible. Rotten eggs mixed with formaldehyde and bitter almonds. The primordial chemistry of the early solar system, preserved in ice for billions of years, and it smells awful. Some comets do more than just sublimate ice. Some have what we call cryovolcanic activity. Cryovolcanic comets erupt near the sun. As they heat up, pressures build beneath the surface, and suddenly, violently, they erupt. Jets of gas and dust burst from the nucleus, sometimes changing the comet's rotation or trajectory. These outbursts can make comets brighten dramatically, flaring in the sky for days or weeks before settling down again. And some comets are bright enough to see in daylight. Comet Neowise was visible in daylight in 2020, during the height of the pandemic. People looked up and saw a comet in the evening sky, visible even in twilight. Its tail stretched across the heavens. It was a reminder that the universe continues, regardless of what's happening on Earth. Comet Neowise came from the Oort Cloud, fell toward the sun, swept around it, and is now heading back out. It won't return for another 6,700 years. But not all comets come from our solar system. In recent years, we've detected visitors from beyond, interstellar objects, passing through on their way to somewhere else. One of these was a comet designated 3 I/Atlas, and it was strange. Interstellar Comet 3 I/Atlas showed strange acceleration as it moved through the solar system. It sped up in ways that couldn't be explained by the sun's gravity alone. This is normal for comets. The outgassing acts like tiny rocket engines, pushing them slightly off course. But 3 I/Atlas accelerated more than expected and in unusual directions. It was small, fragmenting as it went, behaving in ways we didn't quite understand. A visitor from another star, briefly passing through our neighborhood, leaving us with more questions than answers. These comets, whether from our Oort Cloud or from interstellar space, they're ancient, unchanged. They carry information about the early solar system, about the chemistry that led to planets and life. They're time capsules, and everyone we study teaches us something new. But comets are not the only travelers. We've sent our own emissaries outward, spacecraft, carrying human knowledge and ambition into the depths of space. The Voyager probes are perhaps the most famous. Launched in 1977, Voyager 1 and Voyager 2 flew past Jupiter and Saturn, and Voyager 2 continued on to Uranus and Neptune. They sent back the first close-up images of these worlds, revealing moons and rings and storms we'd never seen before. And then they kept going, out beyond the planets toward the edge of the heliosphere. And they carried something special. Voyager probes carry golden records, phonograph records plated in gold, containing sounds and images from Earth, music from different cultures, greetings in dozens of languages, sound of wind, rain, animals, laughter, images of people, places, mathematical and scientific diagrams. A message to anyone who might find them billions of years from now, when the sun has died and the solar system is no more. The Voyagers are now in interstellar space, having crossed the heliopause, the boundary where the solar wind gives way to the interstellar medium. They're the farthest human-made objects, still sending back faint signals, though their power is fading. In a few more years, they'll go silent, but they'll keep traveling, carrying those golden records for millions of years. Silent ambassadors from a small blue world. Before the Voyagers, there were the Pioneers. Pioneer 10 and 11. Pioneer 10 was the first spacecraft to travel through the asteroid belt. There was genuine concern that it might be destroyed by collisions with debris. But Pioneer 10 proved the asteroid belt safe. It passed through without incident, showing that despite the name, the asteroid belt is mostly empty space. The asteroids are spread so thinly that you could travel through it and never see one up close. Pioneer 10 then flew past Jupiter and continued outward, also carrying a plaque with a message for any future finders. And more recently, there was New Horizons. Launched in 2006, it spent 9.5 years traveling to Pluto. In July 2015, New Horizons flew past Pluto and revealed a world of stunning complexity. Mountains, glaciers, a hazy blue atmosphere, the nitrogen ice heart. Pluto was alive, geologically active, far more interesting than anyone had expected. But New Horizons didn't stop there. It continued into the Kuiper Belt, and on New Year's Day 2019, it flew past another object, Arrokoth, a small, distant, reddish object shaped like a snowman. Two lobes gently joined together. New Horizons flew past Pluto and Arrokoth, giving us our first close looks at these distant worlds. Arrokoth is the most distant object ever visited by a spacecraft, over 4 billion miles from the sun when New Horizons arrived. And New Horizons is still going, still functioning, heading outward into the Kuiper Belt, sending back data on the space environment, perhaps finding more targets to study. These missions, Voyager, Pioneer, New Horizons, they represent humanity's reach, our desire to explore, to understand, to go beyond the familiar. They're small, fragile machines in the vastness of space, but they carry our curiosity with them, and they remind us that we're not just observers. We're participants. We've touched these distant worlds, if only briefly. We've sent pieces of ourselves outward into the dark, to see what's there. Rest in that thought. Somewhere out there, right now, the Voyagers are traveling through interstellar space. New Horizons is coasting through the Kuiper Belt. Probes orbit Mars, Saturn, Jupiter. Rovers drive across Martian deserts. We're exploring, we're learning, and we're just beginning. There's so much more to discover. So many worlds we haven't visited. So many questions unanswered. But we're asking them. We're reaching out. And that's something to be proud of. Let yourself feel that connection. You're a part of a species that builds machines to visit other worlds, that sends messages to the stars, that looks up and wonders, and then goes to find out. Breathe slowly. Let the wonder settle. The universe is vast, but we're here, thinking about it, exploring it, trying to understand. All is well. The missions continue. The discoveries unfold. And you're here, learning about them, connected to it all. Rest now. Let these thoughts drift gently through your mind. Comets and spacecraft, messages and mysteries, all part of the grand story of exploration. The journey is nearly over, but the discoveries never end. There's always more to find, always another horizon. Sleep if you'd like. Dream of distant worlds and ancient comets. Dream of golden records spinning through the void. Dream of what we might find next. We've traveled through space. Now let's travel through time. Not backward, but forward, far, far forward, to see what awaits our solar system in the distant future. Nothing lasts forever, not even stars. The sun that warms us, that makes life possible, that has shone steadily for 4.5 billion years. It too will change. It too will die, but not for a long time yet. The sun will become a red giant in 5 billion years. 5 billion years from now. It's difficult to comprehend such a time scale. Human civilization is only a few thousand years old. Our species has existed for perhaps 300,000 years. 5 billion years is almost incomprehensible. And yet it will happen. Here's what will occur. The sun is currently in its main sequence phase, fusing hydrogen into helium in its core. But hydrogen is finite. Slowly, over billions of years, the hydrogen in the core is being consumed. Eventually, in about 5 billion years, the core will run out of hydrogen fuel. When that happens, the core will contract under its own gravity. Heating up, the outer layers will expand. Dramatically, the sun will swell. It will grow larger and larger, becoming a red giant. Its outer layers will extend past Mercury's current orbit, perhaps past Venus. The sun will become hundreds of times larger than it is now, cooler on the surface, but vastly more luminous overall. And the inner planets, Mercury and Venus, may be engulfed, swallowed by the expanding sun. They'll spiral inward through the sun's outer atmosphere, friction slowing them until finally they're consumed, vaporized, returned to the plasma from which they came billions of years ago. And Earth's fate remains uncertain. We don't know if Earth will be engulfed or not. The calculations are delicate, depending on how much mass the sun loses as it expands, how much Earth's orbit expands in response. Some models suggest Earth will survive, just barely, orbiting outside the sun's swollen photosphere. Others suggest it too will be consumed. But even if Earth survives in orbit, it won't be recognizable. Long before the sun becomes a red giant, it will grow hotter. In perhaps 1 billion years, the sun's increasing luminosity will boil away Earth's oceans. The atmosphere will be stripped away. Earth will become a dead, scorched rock, baked by the intensifying heat. And if Earth does survive the red giant phase, it will orbit a white dwarf. After the sun sheds its outer layers, what remains is a core, a dense, hot ember about the size of Earth, slowly cooling over trillions of years. A white dwarf, the planets that remain, perhaps Earth, Mars, the gas giants, the ice giants, will orbit this fading remnant, circling a dying star in a cold, dark solar system. But that's billions of years away. For now, the sun is stable. It will remain so for our lifetimes, for millions of generations to come. There's no need to worry. The future is vast and we have time. So much time. Let's think about time in another way. Think about the outer planets and how slowly they move. We experience a year as 365 days. One trip around the sun. We're used to that rhythm. But the outer planets, their years are so much longer. Neptune takes 165 Earth years per orbit. 165 years. Neptune was discovered in 1846. It completed its first full orbit since discovery only in 2011, just one Neptunian year ago. Think about that. If you lived on Neptune, you'd be incredibly young by local standards. Neptune has only orbited the sun a handful of times since the solar system formed. And the seasons on the outer planets, they last for decades. Uranus seasons last over 40 years. Because Uranus is tilted on its side, its seasons are extreme. When the North Pole points toward the sun, it receives 42 years of continuous sunlight. Summer lasts for 42 years. Then autumn, then winter, another 42 years of darkness. Spring, then back to summer. Each season spanning more than a human lifetime. Imagine living with seasons that last longer than you do. Imagine being born in spring and dying before summer arrives. That's the time scale of the outer planets. Slow, patient, moving through the cosmos at a pace that makes human life seem like a flicker. And yet, on these time scales, even the distant future becomes approachable. 5 billion years is a long time, yes, but the solar system has already existed for 4.5 billion years. It's lived most of its life already. The end is perhaps closer than the beginning, in some sense. But don't let that sadness touch you. 5 billion years is still an eternity. In that time, so much can happen. Life could spread to other worlds, other star systems. Humanity, or whatever we become, might outlive the sun itself, moving on to orbit other stars, carrying the legacy of Earth with us. Or perhaps we'll find a way to save the Earth, move it outward bit by bit, keeping it in the habitable zone as the sun grows. Or build habitats in space, independent of planets, free to travel wherever we choose. The future is long, and it's unwritten. The sun will change, yes, but we don't have to simply accept what comes. We can adapt, we can endure, we can continue. And even if we don't, even if humanity is long gone by the time the sun becomes a red giant, that's okay, too. We were here. We looked up at the stars and wondered. We built telescopes and spacecraft. We learned the story of the solar system, from its birth to its eventual end. We understood. And that understanding is a kind of immortality. The solar system will outlive us. The universe will continue long after the sun fades. But we were part of it. We were here in this brief moment between the formation of the solar system and its end. We existed. We mattered. Let that be enough. Rest now. Let the vast time scales wash over you. Let the slow orbit of Neptune, the long seasons of Uranus, the distant future of the sun, let it all remind you that time moves differently at different scales. What seems urgent today will be forgotten. But what we learn, what we discover, what we understand, that echoes forward. You are here now, in this moment. The sun is shining. The planets are turning. The moons are orbiting. Comets are falling inward from the Oort Cloud. And you're thinking about it all, holding the entire solar system in your mind. That's beautiful. That's enough. Breathe deeply. Let go of any worry about the future. 5 billion years is a long time. For now, rest. Be here. Be present. The solar system continues. And so do you. For now, that's all that matters. Sleep if you like. Dream of red giants and white dwarfs, of slow-moving planets and endless seasons. Dream of time stretching forward and backward, vast and patient. We've traveled far together, from the sun at the center, outward through the planets, past the moons and dwarf planets, all the way to the Oort Cloud at the edge of everything. We've moved through billions of years of time, from the solar system's birth to its distant future. And now, as we come to rest, let's reflect on what we've seen, on what we know, and on what we still don't know. Nearly 1 million asteroids orbit the sun. 1 million. We've cataloged them, tracked their orbits, given them designations. Some are large, hundreds of miles across. Most are small, just rubble, fragments from ancient collisions. They orbit mostly in the asteroid belt, but some wander into the inner solar system, crossing Earth's path. Some drift outward into the realm of the giant planets. 1 million asteroids, each one unique, each one a piece of the early solar system, preserved in stone and metal. Some are rich in iron and nickel. Others are carbon-rich, dark and crumbly. Some may contain water, locked in minerals. They're resources, potentially, building materials for future space habitats, stepping stones to the outer planets, or simply objects of study, teaching us about how planets form and evolve. 1 million asteroids, and we visited only a handful up close, landed on a few, brought samples back from even fewer. There's so much more to explore, so many worlds, even among these small, rocky fragments. And then there are the things we've only theorized about. Diamonds may rain on giant planets. Deep inside Jupiter, Saturn, Uranus, Neptune, beneath the clouds, beneath the layers of hydrogen and helium, there may be conditions where carbon is compressed into diamond, crystals forming in the crushing darkness, then falling like rain toward the cores, accumulating over billions of years into layers of diamond, miles thick. We can't see it directly. We can only infer it from models and experiments. But the physics suggests it's real. Diamond rain, on worlds where no eye will ever see it. A hidden wonder happening now, as it has for eons. It's humbling, isn't it? To know that there are things happening in the solar system that we'll never witness directly. Processes so extreme, so alien, that we can barely imagine them. And yet they're real. They're happening. The universe doesn't need us to observe it to be extraordinary. And there's the Great Red Spot, that ancient storm on Jupiter. The Great Red Spot still shrinks, but survives. We've watched it grow smaller over the past century. It used to be large enough to fit 3 Earths side by side. Now it's perhaps 1.5 Earths across. It's shrinking for reasons we don't fully understand. Changes in Jupiter's atmosphere, shifts in the jet streams that sustain it. Will it disappear entirely? We don't know. Maybe Maybe it will fade away in another few decades, and Jupiter's face will change. Or maybe it will stabilize, persist for centuries more. We're watching, waiting, observing a storm that has outlasted everything in human history, wondering if we'll be the generation that sees it end. But even if it does disappear, Jupiter will create new storms. The planet is dynamic, always changing, always churning. The great red spot is extraordinary, but it's not unique. It's just one storm among many, one feature in an ever-changing atmosphere. And that's the thing about the solar system. The more we learn, the more we realize how much we don't know. Many solar mysteries remain unsolved. Why is the sun's corona so hot? What exactly is happening inside the ice giants? Are there more planets beyond Neptune, hiding in the dark? What disturbed the Oort Cloud to create the heavy bombardment that scarred the inner planets billions of years ago? Is there life in the oceans of Europa or Enceladus? Could simple organisms survive in Titan's methane lakes? Did Mars once have life? And if so, where did it go? We don't have all the answers. We may never have all the answers, but we're asking the questions. We're looking. We're exploring. And every answer leads to new questions, deeper mysteries, further horizons. And here's the remarkable thing. We've explored only a fraction of our own cosmic backyard. We've sent probes to all the planets, yes. We've orbited some, landed on a few. We've visited asteroids and comets and dwarf planets. But compared to what's out there, we've barely begun. There are hundreds of moons we've only seen from a distance. Thousands of asteroids we've never studied. Millions of Kuiper Belt objects we've never observed. The Oort Cloud is almost entirely unexplored, known only by inference. And that's just our solar system. Beyond that, there are hundreds of billions of stars in our galaxy alone. Many of them have planets, perhaps trillions of planets in the Milky Way, and billions of galaxies beyond that. The universe is vast beyond comprehension, and we're here on one small world, looking out, trying to understand it all. But we've made progress, remarkable progress. A few hundred years ago, we didn't know planets orbited other stars. We didn't know the solar system formed from a cloud of gas and dust. We didn't know about the Kuiper Belt or the Oort Cloud or the Great Red Spot or the oceans under Europa's ice. Now we know. We've learned. We've explored. And we're still learning, still exploring every day. There's something deeply comforting about that. No matter how much we discover, there's always more. The universe will never run out of wonders. There will always be new questions to ask, new places to explore, new things to understand. And you're part of that. By being curious, by listening to this, by thinking about the solar system and the universe beyond, you're participating in that grand human project of understanding. You're connected to everyone who's ever looked up at the night sky and wonder what's out there. From ancient astronomers charting the movement of planets, to Galileo turning his telescope to Jupiter's moons, to the engineers who built Voyager and New Horizons, to you, right now, learning about these distant worlds. You're all part of the same story. The story of exploration, of curiosity, of wonder. So rest now. Let that wonder fill you. Let it be a gentle, comforting presence. The universe is vast, yes, but you're here. You're thinking about it. You're part of it. The sun continues to shine. The planets continue to orbit. The moons continue their dances. The asteroids tumble through space. Comets fall inward from the darkness, and somewhere on a small blue world, you're lying here, thinking about it all. That's enough. That's beautiful. Breathe slowly. Let your thoughts drift like solar wind, outward into the calm. Let the solar system turn in your mind, all its pieces moving together in their ancient rhythms. You are made of stardust. You are part of this cosmic story. And you're here, now, connected to everything. All is well. All is wonder. All is calm. Sleep now if you like. Dream of planets and moons, of ice and fire, of storms and silence. Dream of the solar system, turning slowly in the dark, beautiful and patient and eternal.